Okay, so the very last thing that I am going to be going over is um salts, salt hydrolysis, and buffers. So these aren't anything that are like completely new. They're basically just more specific concepts and applications of the material that I've already gone over. So salt hydrolysis has to do with obviously the breaking down of a salt when you put it in water. So salts are ionic. They are between a metal and a non-metal, which means that they dissociate or ionize in water. So we're going to use NaCl again as an example. So if you put NaCl into water, it's going to ionize into Na plus and Cl minus. Now we have three um different types of salts. So neutral, acidic, and basic. And how you determine whether a salt is neutral, acidic, or basic is by looking at which acids and bases um need to have reacted to form that salt. So again, using NaCl as an example, um, in the previous video, I talked about neutralization reactions. So if you think back to that, the neutralization reaction to result in NaCl as a salt is hydrochloric acid and sodium hydroxide, resulting in water and obviously the salt NaCl. Now, when we look at these parent acids, you should by now know that hydrochloric acid is a strong acid. We're going to put an S for strong. And then sodium hydroxide is also a strong base. So when the parent acids and bases of a salt are both strong, that always results in a neutral salt. Now, if we had a strong acid but a weak base, that would result in a acidic salt, and vice versa. If we had a weak acid and a strong base, that would result in a basic salt. Now, obviously, there are also scenarios where there would be a weak base and a weak acid. Sorry, I said that the other way around. Um, but we don't have to know this for the purposes of honors chemistry. But just to put it out there, if you did have something like that, you would have to look at the relative Ka and Kb values. If you remember, that's how we measure the strength of a weak acid or a weak base. And then whichever one was higher, that is what the salt would be. So if the Kb was higher than the Ka, then that would also result in a basic salt. But don't worry about that for this unit. Okay, now moving on to the final thing, and that is buffers. So buffers are basically a system in which the pH of the solution can be shifted from acid to either more acidic or um more basic. Or honestly, a better way to describe this is either as more or less acidic or basic. Um, so an example of a buffer system is carbonic acid. So carbonic acid is a weak acid, and buffers always have to do with either weak acids or weak bases. And we know that if we have a weak acid, or a weak base, the forward and reverse reactions are happening. So this means that the weak acid is not being completely ionized. And again, just to review, if, for example, you had a problem saying that, what is the strength of, what is the pH of a solution that has zero point 0.1 molar concentration of carbonic acid? You cannot you cannot plug in this zero point 0.1 into the pH equals negative log of the concentration of hydrogen ions. You cannot plug this into this. This does not equal this, okay? You would have to use those ice tables and then find the concentration of hydrogen ions from there using the Ka formula, and then from there you can plug it in to the pH formula. However, if it was a strong acid like hydrochloric acid, and then that said you had a molarity of zero point 0.1, you can go straight from the zero point 0.1 molar concentration of the acid to the pH formula. Just bringing that up again. Anyway, let me restart it. Okay, so as we know, when you have a weak acid, the weak acid exists both as the acid itself, so not ionized, and its ionized version. And that is again that's why we have the forward and reverse arrows. Now, buffers also always consist of the weak acid, like we have here, and its conjugate base. And if you remember, according to the Bronsted-Lowry model, a conjugate base is the acid, however, it has one proton less. In this case, carbonic acid is H2CO3. Take away a proton, you're left with HCO3 minus. So, yeah, okay. Now, the thing about buffers is that, like I said, that they can shift the pH of a solution. If we think back to our equilibrium unit, if a system is in equilibrium, we can shift that equilibrium by applying a certain type of stress to it. So, and that has to do with like following Le Chatelier's principle and all that. So, if we have a buffer system, for example, this carbonic acid example, and we increase the amount of hydrogen ions in that solution. So the amount of hydrogen ions increases. Now, this side of the reaction is having a stress placed on it. And to relieve that pressure, we're going to be forming more carbonic acid. So, and by doing this, the buffer helps lower the pH. Again, if you've taken AP Bio, this is like a natural thing that your body does to help regulate the pH of your blood, urine, anything. So yeah, that's basically all you have to know about buffers. Obviously, carbonic acid is not the only one, but yeah, pretty much it.